Hey Nick, ready to learn about pushdown automata? Before we get into it, you're going to need a good foundation in regular languages, DFAs, and NFAs.
Yeah, I've got those down. State to state, no memory, just following the arrows.
Good. What about using the pumping lemma to prove a language isn't regular?
Easy. You can't pump because the machine can't remember what it's seen.
Perfect. And context-free grammars, variables, terminals, and replacement rules?
Yep, I'm comfortable with CFGs.
Well, Nick, sounds like you're ready. Let's look at this language L of strings with equal zeros followed by equal ones.
Like these two examples? Seems simple enough. Can't a DFA handle that?
Let's try. A DFA reads left to right, one symbol at a time.
It's reading the zeros, looked fine so far.
Yeah, now it hits a 1, but how many zeros did it just see? It has no way to remember.
Wait, it just forgot? It can't store a count anywhere?
Exactly. A DFA just doesn't have memory. There's no scratch paper to keep count.
So for any DFA with k states, I could just feed it k plus 1 zeros and it would be lost?
That's the idea behind the pumping lemma. A basic machine can't just keep counting forever. We need something more.
So what's the solution? What gives us that memory?
Let's stick to deterministic PDAs today. They're defined by a 5 tuple, which just means 5 parts. Let's build one.
Five parts. Alright, what's first?
The input alphabet. These are the symbols on the tape that the machine reads, like zeros and ones.
Got it. What about the stack?
The stack alphabet. It includes symbols the machine can push and pop, plus the bottom marker.
And what about the states?
The set of states. These are the different modes the machine can be in, like Q0 or Q1.
Where does it start?
The start state, Q0. That's where the machine will begin its computation.
And what connects everything together?
The transition functions, just like a rulebook. One last thing, at the end of the tape, we'll always have the square, and at the bottom of the stack, the dollar sign, meaning it's empty.
So tell me more about this transition function.
The transition function, we read 3 inputs to decide a remove.
3 inputs, what does it look at?
The current state, the tape symbol, and the top of the stack.
And what does delta produce as output?
3 things, the new state, the head direction, and what replaces the stack top.
So I remember hearing that when we view what is on the stack, it gets popped off. If we wanted to add something to the stack, we'll be adding that piece back and then a new stack item. Is that true?
Exactly. If the replacement is empty, we pop. If it's a dollar sign plus an S, we put the dollar sign back plus an S on top.
Can you walk me through this?
Sure. Let's look at a filled out PDA. Take this rule. We read an A in the start state with the dollar sign on the stack.
So what happens after the transition fires?
We stay in the same state, move the head right, and push an S on top of the dollar sign.
I'm finally getting it.
Let's balance some parentheses. A is open and B is closed.
Got it. So for A, we push an S.
State Q stays the same, and we go again with A.
Now we got a B. Do we pop to match?
Yep, one S comes off the stack.
It's the last B on the tape. What happens now?
We pop again. Every opener is matched.
Tape is at our square, and we're down to the $sign.
Perfect. The stack is empty, so the machine accepts.
Fantastic. Now how will this get me a job?
That's for the next video.